Hello and welcome to your lesson on function friends, transformations, and inequalities. So, my function friends are functions that are general functions that you should be able to use pretty easily. And these are things that you may have learned in a pre-calculus course. You should be familiar with what the graphs do and how the numbers behave. So let's take a look at a few function friends where you should be pretty familiar with the shape of the graph. So we have one of our best friends, as you'll remember from the last lesson, y equals x. So anything with a linear equation, you will have an x and you will have a y and you will have only a single power of x. Okay, so it would only be x to the first or perhaps x to the 0. Next function friend, we have y equals x squared. So y equals x squared is a shape, makes a shape called a parabola. Our next function friend that we have been looking at, we have been looking at some things that have absolute values in them. So when we look at the graph of y equals the absolute value of x, well, if we look at numbers that are bigger than 0, that would just be the line y equals x. So as we said, we could write this as a piecewise function. So y equals x when x is greater than or equal to 0. And it's equal to the line negative x when x is less than 0. So positive x's get left alone, negative x's get negated. So it turns out to look something like a triangle. And the more absolute values you add in, the more different bends you will have in your equation. Sorry, in your function. So our next function friend is y equals radical x, which looks kind of like half of a sideways parabola. In fact, if we wanted to get that whole sideways parabola, we would be writing x equals y squared, because that is the, quote, inverse. It's not a function, but it is the thing that reverses the squaring process. That would be the positive and the negative square root. So x equals, and we'll talk a little bit more about inverse functions later in the course. So there is our y equals radical x. Okay, and these are just our basic functions that are starting at the origin, and they haven't really been expanded, stretched, compressed. They're about the simplest you can get when it comes to these functions. We also have our friend, the cubic function. So our cubic function is y equals x cubed. That goes up like that. Okay, it's a very steep thing. And just like the parabola, we have our x squared and we have our square root of x. We also have a cube root of x. So y equals the cube root of x. It's actually just this cubic function reflected over the line y equals x because it is our inverse. So it looks like this. Okay. So we have also some reciprocal and some rational functions. Okay. So we have our, so let's look first at just a basic reciprocal function. We have y equals 1 over x, and that looks like this. It's what we call a hyperbola. And if we take the reciprocal of a function like y equals 1 over x squared, that one looks like this. So why are we so interested in being able to draw these basic graphs of functions? Well, if we look back at all of our functions, what happens is, and this is the thing, we're going to just take a big picture look at all of these functions. Okay, maybe not quite that big. Let's go back a little. So we can look at all of our function friends that are graphs that we should be relatively familiar with. And there's a couple of reasons why it's good to know what these basic functions look like. okay? The first one is that when we're looking at the graphs, and this I'm going to write over to the side, and I'm going to write it really big compared to these graphs, because this is so important, and it's something that people can get a really long way through math. They can graph a ton of functions, and they still don't fully understand. And that is y equals f of x. What does this mean? So when we look here at y equals x, there are two things we can think of. First of all, any points here on this line are going to satisfy whatever our equation is, y equals some function that happens. The second thing is that when we look at the graphs, we can actually tell what's happening with the function. So let's take a look in depth at what does this y equals f of x mean when we're looking at a particular function. So let's look at y equals 1 over x. So we can see that as we get close to 0, so if we take a walk along the graph, we see along the graph our y values are getting bigger and bigger and bigger as we get closer to 0. What this means is that the numbers here in the equation, as we plug in x's that are closer and closer and closer and closer to 0, the numbers get bigger and bigger and bigger and bigger. So if you take and if we go here and we plug in bigger and bigger and bigger and bigger numbers, keep walking along the function, that y value is going to get closer and closer and closer and closer to 0. And so that means as we take 1 over progressively bigger numbers, our answers are going to come out as closer to 0. So looking at the picture, and then what we can see is that as we jump to very, very small negative numbers on the other side, it's going to make very, very negative numbers as we're taking 1 over those very, very, very small negative numbers. We get very, very, very large negative numbers. And as we take bigger and bigger negative numbers as x, we plug that in and we get progressively smaller and smaller and smaller outputs for 1 over x. So this is something that we can use as we get to more complex equations. So let's take a look at one way of looking at slightly more complex equations. Now we're going to get full into graphing during our applications of derivatives unit, but we're going to start with some of the things that we do know about equations. So if we have a function, okay, and we have y equals f of x. We can take that basic function, like those 8 we just had a look at, and there are other basic functions. We don't necessarily explore every basic function. We can take those basic functions and we can stretch them, we can shrink, we can kind of squash them, we can move them around in the coordinate plane, we can flip them over the x-axis, we can flip them over the y-axis. So we can do all kinds of things. So if you recall, we have some basic transformations we can perform on a function. So we have, if we take f of x and we map it to a f of x, okay, so we're multiplying the whole function by some number. We're multiplying the function acting on x by some number. This gives us a vertical stretch, a vertical compression, and possibly also a reflection in the y-axis. Sorry, in the x-axis, in the y direction, but in the x-axis. So what values of a will stretch that function, compress that function, and reflect that function? Well, I recommend, I'm going to give you a little exercise to do. I'm not going to do it, So as I told many of you in class, your best friend is www.desmos.com. It is a free online graphing calculator that really can help you deepen your understanding of how graphs and how functions relate to each other. So go to Desmos, www.desmos.com. Pick one of your function friends. If you're not sure, I recommend perhaps y equals x squared. Perhaps if you're feeling a bit more adventurous, you might want to try y equals the cube root of x. You can pause the video, or you can wait till we go through all the different transformations and try them out yourself. So what I want you to do then is go and try some numbers. So try putting some numbers right in front of the x squared. Try putting some numbers right in front of the cube root of x. What happens if you try big numbers? What happens? So if you try positive numbers versus negative numbers, what happens if you try fractions? What happens if you try 0? So look at what those numbers do, and then try to figure out what values of a are going to produce what numbers. Okay, so what if you don't want to stretch, compress, or reflect in the in sort of the y direction, in that vertical direction? Well, if you want to do it in the x direction, we are going to look at what happens when we take f of x and we map it to f of bx. So we're instead multiplying the x by some number b. And this is going to cause a horizontal stretch. I believe the technical term is expansion, but I do rarely use that. A horizontal compression, and compression may be referred to as a squish as well. That is a very technical term. And it may have a reflection in the y-axis. So it changes it's going to change x coordinates. So I want you to look at what values that's going to make a difference for. Look at these same, go to Desmos and see if you can figure out for what values of b will give you a stretch, what values of b will give you a compression, and what values of b will give you a reflection in the y-axis. And don't worry, at the end I will give you all of those things. We will go back and we will fill in which values. But at first, I would like you guys to test that out on your own. Similarly, we are going to look at when f of x is mapped to f of x minus c. What happens when we subtract a number from the x? What if we're adding or subtracting to something in the x? And this is going to give you some kind of horizontal translation. So generally, things that are happening to the x are going to change your outputs. And when you're doing things to the x, it's going to change things in the x direction. So it's going to stretch or shrink in the x direction. It's going to shift in the x direction. And when you're changing things outside the function, you're going to be changing things in the y direction. Okay. And so when you do something like f of x plus d, this is going to give you a vertical translation. Okay. So I urge you to go and try doing some of these to one or both of these two example functions on Desmos to see what is it doing geometrically to the graph that you have. And first you can try these one at a time and then see what happens when you try them together. And then see how does the order matter? What happens if you're multiplying by b first before you subtract c? How much does that shift it? How does that work? Okay, so these are things that the rules were come up with by people investigating it. So I really do urge you just to go and to investigate it. Okay. So here is our big translation formula. We have y equals a f of b times, in brackets, x minus c. We have double brackets. If we don't like that, we can always put a lovely square bracket, plus d. Okay. And in this case, A, okay, so I told you I would give you the answers at the end. So please, if you haven't done the Desmos thing, go do it first before you get the answer, because that's how you're going to learn. And once you've done it, pause it, go check, then come back and have a look. Okay? Everybody has done the Desmos activity at this point. I will be checking. Okay, so here, this value of A, if it is A greater than 1, so if we have a positive number that's bigger than 1, we have a vertical expansion or a stretch. Okay? If we have A between 0 and 1, then we have a vertical compression. If A is between -1 and 0, then we have a vertical compression plus a reflection. In the x-axis. And if we have A less than -1, we have a vertical stretch plus reflection in the x-axis. So A determines both our vertical stretch or compression, sort of like a scale factor, how much are you pulling and pushing and pulling in the y direction, as well as whether you're flipping over the x-axis in the y direction. B, right here, determines similar things but for x. But because it's acting on x, what I like to think of is larger values of b speed up what's happening to the function, which gives you a horizontal compression. So if we have b greater than 1, so if we have a larger number there, okay, we are speeding things up, so we get a horizontal compression, which is the opposite of what happens with our a's. And if we have b between 0 and 1, we get a horizontal stretch. So that's actually like slowing it down. So the function, things are just not happening as quickly if you're kind of walking along the function. If we have b between -1 and 0, it is the same thing. It's a horizontal stretch plus a reflection in the y-axis. So it's the y-axis, but it's really your x coordinates that are getting flipped. And then b between b just being, sorry, less than -1, we get a horizontal compression plus a reflection in the y-axis. Okay, so if it's a reflection in the y-axis, remember you're reflecting x coordinates, you're negating those x coordinates. So one thing you might have noticed is that changing b for y equals x squared didn't actually change anything. You could change what the x was inside the brackets, and you would do like -2 in brackets, -2x in brackets squared, and you would still get a positive number. So one thing just to be aware of is that that's going to happen. So if you have something that's symmetric about the y-axis and you are and you're going to try to reflect it in the y-axis, nothing is going to happen. So think about what graphs it doesn't actually matter with, and maybe some of the graphs up there that it doesn't matter. Y equals 1 over x is a very interesting one if you want to go play around on Desmos, because that one, compressions in x and compressions in y actually do the same thing. And you can go and see, whereas mostly for a lot of functions, a stretch in y is the same as a compression in x. And you can, again, go and check, how does that work out algebraically? How can you show that a horizontal compression for some functions can actually be written as a vertical stretch? So for a parabola, for instance. And those are all interesting ways to sort of take your understanding of these transformations to the next level. Okay, next we have this C. So C is, we have a horizontal shift C units right, and there's no complications there. So if you are moving negative C units right, you are moving left. So positive, if it's x minus something, you're moving right. If it's x plus something, you're moving left. And here we have a vertical shift of d units up. Similarly, if you are going negative d units up, that means you are going d units down. Okay. Last bit. So now that we have a little bit of a sense of what our transformations are, how those work, and hopefully you guys have done some experimentation on your own, because that's how it's really going to start to make sense, is if you try some of these things and see what your changes do in the graphs, and come prepared with questions about, I changed this in my function. Why did it work out this way? I thought it was going to work out this way. These are excellent things to talk about in your study groups. But for now, we're going to look at how do these things that we understand, so y equals f of x, what we see in the equation, what we see in the graph is telling us what's happening with the numbers. Our function friends, we know what these functions look like, basically what they look like, and our transformations and what we understand about these functions. So we're going to look at a couple examples with parabolas and some rational functions, and then think about what is happening. So, example 1. We have negative x squared plus x plus 6 is greater than 0. Now, I want to work with positive numbers, so I'm going to multiply both sides of this equation by -1. So I get x squared minus x minus 6 is less than 0. Okay? So the first thing I'm going to do is I'm just going to kind of sketch here. What does this look like? It's got an x squared in it, so I know it looks kind of like a parabola. And when I'm sketching a parabola, one of the things I'd like to know, I could try to find the vertex, but I don't really feel like completing the square or reviewing it right now. So I'm going to try to find where the roots of the parabola is. Because there is a 1 out front, or it's a positive number, I know it's an upward opening parabola. We do not have a reflection here in the x-axis. So what I'm going to do is I'm going to try to find the roots of this parabola. So if I think of this as a function, y equals x squared minus x minus 6, the roots of this parabola is where 0 is equal to x squared minus x minus 6. And this is going to help tell us where this is going to be negative, because y equals x squared minus x minus 6. The y values tell you what's happening with the numbers. Where the y is negative, or where the graph is below the x-axis, is going to be where the numbers come out negative. So y equals f of x. Y is actually equal to that function. So let's see where it actually hits the x-axis. So we can factor this. We get x minus 3 and x plus 2. So we know that equals 0, so 0 equals 3 and -2. So we have -2 and 3. So we have a parabola, and we know it's upward opening. We know it comes like this. So we can see that between -2 and 3 is where it's negative. So x is going to be greater than -2 and less than 3. But Miss Eaton, I don't like graphs. How do I solve this algebraically? Well, you're going to have to think, again, you still have to do this process over here. You have to think about where this is equal to 0. Because where it's equal to 0 is going to be where it changes from being positive to negative and negative to positive. So if you want to think about it on a number line instead of a graph, We have our numbers, sorry, at -2 and +3. So we have to look at what's happening when x is less than 3. Again, I'm mixing up my 2's and my 3's. X is less than -2. X is between -2 and 3, and x is greater than 3. Okay, so what we can do is we can think about each of these factors. So we have x minus 3 and x plus 2, and then we can think about their product. And this is going to be a useful technique when we get to more complex equations, x minus 3, x plus 2. So we have two things and we're multiplying them together. So I'm going to think about when each of these factors is positive and when it's negative. So when x is less than -2, we get x minus 3 is negative, and x plus 2 is also negative. So a negative times a negative gives us a positive. But positive isn't the answer we're looking for. We're not looking for when this product is positive. So here, between -2 and 3, x minus 3 is definitely still negative. So you can pick a number, 0. Minus 3 is definitely negative. X plus 2 now is positive, though. So a negative times a positive is going to give us a negative. This is one of the regions we're looking for. Now we go greater than 3, x minus 3, any number bigger than 3 will give us a positive, x plus 2 will get a positive, and we get a positive for our answer. Okay, so as this video is getting a little bit long, I'm going to carry on the next examples into a different video that will be posted shortly. So this is, consider this part 1, and part 2 of lesson 5 will be coming shortly. Thank you.